A closer look at repetitive shock vibration from Qualmark, the world leader in accelerated stress testing. Qualmark systems are designed to provide extreme thermal and vibration stresses that will rapidly and effectively expose weaknesses in a product's design or manufacture. Typically, reliability engineers think of electrodynamic or ED vibration systems for delivering vibration stress. The stresses and fatigue induced by ED shaker vibration are well understood. In highly accelerated life testing, repetitive shock vibration is used. An RS vibration system consists of a semi-rigid table and understructure with several pneumatic actuators that are mounted to the underside of the table. The table is driven by continuous repeating shocks from these actuators. When using an ED shaker, the table vibration is the only mechanical stress delivered to the product. The final excitation to the product is the tabletop vibration, filtered by the fixture and product transfer function. With an RS vibration system, the product is excited not only by the vibration of the table, but also by the shocks transmitted to the product. The shocks cause all components in the product to ring at their own resonant frequencies, where fatigue accumulates fastest. These shocks and the resultant resonant excitation are what makes RS vibration so effective for rapidly fatiguing product. Mechanically weak or defective components quickly fail because the shocks produce excitation in all three axes simultaneously across a wide frequency range. The real-time acceleration response from the product clearly shows high acceleration stresses, with peak accelerations that are much higher than are possible using an ED shaker. However, this complex and random product motion can make it difficult to intuitively understand the effects of the shocks on a product. This video, taken with a high-speed camera, makes the effects of these shocks much clearer. As can be seen here, the displacement of the table and fixture for the PCB are very low, but the board's response is much higher. As the board flexes, strain is induced in all the solder joints, particularly for the rigid surface mount components. A closer look at actual component excitation shows that the shocks are making the components move at their own resonant frequencies, in multiple axes. The larger leaded components, with lower resonant frequencies, experience wide excursions as they resonate. Smaller components, with high resonant frequencies, can be seen responding to the individual actuator strikes with a displacement and following ringdown. Much more information can be gained by using motion analysis software on the video. Here you see the software in action, tracking the displacement, velocity, and acceleration at 3 different points on the product: the board itself, the top of a large electrolytic capacitor, and the front of a smaller sugar cube relay. The analysis allows tracking in 2 axes simultaneously. Graphs of the resulting data show the shocks inducing large, slow excursions in the circuit card, even though those low frequencies were not seen in the earlier video showing the tabletop motion. Here is the displacement induced in the large capacitor, in the x-axis and the y-axis. You can see that the shocks are causing displacement in different axes and at different frequencies. Finally, we have the displacement induced in the small relay. Because the resonant frequency of the relay is much higher, it will ring down between actuator strikes, so its displacement is seen as small, high-frequency bursts. PSDs of the acceleration data from these points show that the board is excited at its own resonant frequency, while the small relay shows its high-frequency resonant response, not seen in the board PSDs. By using this high-speed video analysis, The dramatically fatiguing nature of the shocks used in repetitive shock vibration becomes clear. With every component, board, subassembly, and assembly responding at their own resonant frequencies in all three axes, as well as the rotations around those axes, simultaneously, any mechanical defect or weakness in the device will be forced to rapidly fail. By using Halt and Hass with repetitive shock vibration to find these weaknesses and take corrective action, your final product will be more robust and more reliable, resulting in lower warranty costs and delighted customers. Learn how Qualmark can put the power of repetitive shock vibration to work for you.